A very good afternoon to one and all. I take immense pleasure in welcoming all for the first day of the Faculty Development Program on Exploration of Mathematics in Emerging Fields. Welcome the challenges, look for the opportunities in every situation to learn and grow in wisdom. I request Mr. V. Ratanakumar, Assistant Professor and Head, to welcome the gathering.
Warm good afternoon to everyone gathered here. Thank you to each and every one of you for being here with us at this 5-day International Virtual Faculty Development Program. The beginning is the most important part of success. With this note, I express my hearty welcome to our chief guest, Dr. Ismail Naci CANGUL, Faculty of Arts and Science, Department of Mathematics, Bursa, Uludag University, Turkey, for this beautiful occasion. Welcome, sir. It's my pleasure to welcome Dr. N. Muthumani ma'am, Principal of PPG College of Arts and Science, for this wonderful knowledge sharing session. Welcome you, ma'am. I'm very happy to welcome my colleagues, Dr. R. Praveena, Dr. C. Janita Nancy, and Dr. A. Maheshwari of this virtual faculty development program. I express my sincere welcome to the participants from various colleges and universities. Welcome you all. On behalf of our department and my own behalf, once again, I welcome you all.
Thank you, sir. Giving encouragement to others is a most welcome gift, for the results of it are lifted spirits, increased self-worth, and a hopeful future. I request Dr. R. Praveena, Assistant Professor, to introduce our chief guest of today.
It is with great pleasure that I introduce to you our distinguished guest of honor, Professor Dr. Ismail Naci CANGUL, from the esteemed Bursa Uludag University, Faculty of Arts and Science, Department of Mathematics, Turkey. Professor CANGUL's journey in the world of mathematics is not just one of academic brilliance, but also of unwavering commitment and remarkable achievements with 30 years of teaching experience. He began a journey of academic exploration that has made a lasting impact on the field. He has authored an impressive array of scholarly works, including 90 books and over 370 scientific research papers, many of which are indexed in esteemed databases. His collaborations extend globally with colleagues from Turkey to countries as diverse as India, France, the United States, and beyond. In addition to his academic work, Professor has played a vital role in shaping the future of mathematics by guiding and supporting many MSc and PhD students, helping them develop their skills and expertise in the field. He has been honored with numerous scientific awards in recognition of his academic accomplishments. Notable among these are the highest number of annual publication prize in 2011 and 2013, the special prize of Bologna Coordination Committee member in 2011, the highest number of annual projects prize in 2012, Scientist of the Year prize in 2012, the annual Successful Academic Group prize, Mathematics Department in 2012, the Best Performance Award in 2016, and the highest number of annual publication prize among all academicians in 2020 at Uludag University. Moreover, for both 2021 and 2022, he secured the highest points for his academic and administrative contributions within the university. Additionally, he holds records for the highest number of publications as the first author and the highest number of Q1 and Q2 publications in the entire university. He has been continuing editorial positions for 34 international scientific journals and serves as a referee for over 200 journals. Additionally, he has served as an editor and guest editor for prestigious FPI journals such as Advances in Difference Equations, Journal of Inequalities and Applications, Boundary Value Problems, Fixed Point Theory and Applications, and many more. His Web of Science H index stands at 19, reflecting the significance of his contributions to the field. He is a member of 7 national and international mathematical societies, one of which is honorary. Welcome you, sir.
Is it okay now?
Yes, sir. Yes, sir. Thank you, sir.
Very strange. So I'll find my slides. I'm really sorry for
No
this.
problem,
This
sir.
is
No
happening
problem,
for
sir.
the first time.
No problem, sir.
Thank you for understanding. I will open now my slides again. So I hope it's fine, better, much better.
Sir, it is very
I'm
fine now, sir.
good.
It is
good,
very fine now.
perfect.
Thank you so much, sir. Thank you so much.
Well, when you get older, you do strange things. This is one of them, and I don't know why it happened.
Sir,
Because
I swear.
yeah, every day I do some talks almost, and
Yes, sir.
I have that problem. Usually it goes on, but this time I did something wrong. I don't know. I'm
We
sorry.
understand, sir. No
But
problem at all,
I
sir.
will start again. I will
Yes, sir.
start
Yes,
again,
sir. Now it is very, very
summarizing.
clear, sir. So can you
Very
so
good.
that we can move on
Perfect.
confidently. No problem, sir. Thank you so
Thank
much.
you. Thank you very much. I will be feeling easier and relaxed now, because I
Yes,
was
sir.
hearing my voice and I had to wait till it's finished. I was talking like the ones in adverts sometimes. Anyway, okay.
Okay.
Graph
Okay,
theory,
sir.
I will be talking today. And before I start my slides, I will be giving you some ideas about why people study graph theory. Because we study graph theory, because we can model. Modeling is very important, nowadays. We can model real life examples in our lives, in our laboratory, in our city, in our universe, in our brain, anywhere, from micro to micro. Everywhere we can use graphs to model some things, some real life situations. For example, a city map can be modeled by a graph. Like a metro map, metro plan, a subway plan in your city or in some city, there are dots, circles, small circles for each station, and between them there are lines. The length of these lines, edges, are almost similar, equal. They don't reflect the real distance between the stations, usually, okay? So the important thing is, what is the next station and what was the previous station? These maps, these graphs denote only this information. They don't say you that between these two stations, there is how many kilometers. You don't know. Or is it a shopping area, or is it a rural area? What about the surroundings? It doesn't give you any information. So just the relations, which dots, which vertices are related. We use this in city maps, in networks nowadays, in social media, in all networks, actually, communication, transportation, this kind of networks, electronics, in chemistry, physics, neuroscience, medicine, biology, everywhere in social sciences, everywhere we have relations in our lives, okay? So we can model these relations and these situations by graphs, by putting for everyone for every city, for every person, whatever is your subject, by putting a vertex. Okay? And if two vertices are connected to each other, then in your graphs, this in the real life situation, or these two subjects are connected somehow. If there is no line between them, if there is no edge between them in your graph, then that means these two subjects are not related to each other. Okay? For example, three persons, you think, three people, are meeting in some room. One of them knows the other two. So this one is related, this one is connected to this other two. But these two people that the first one knew do not know each other. They have not met any time before. Okay? So there is no line between them. So only from the person who knows the other two persons to the other two persons, there are lines. Okay? This is a path graph, for example. So according our needs, according our modeling, we form different types of graphs. This could be cyclic graphs, this could be complete graphs, this could be wheel graphs, this could be friendship graphs, this could be fun graphs, this could be path graphs, null graphs, whatever. There are maybe hundreds of ways of introducing such graphs. We study graphs by mathematics, naturally, because graph is a figure consisting of vertices, some of which are connected to each other by edges. Okay? This is just a children's drawing. Very easy. Just put some dots, some vertices, and connect some of them. Okay? It's like a puzzle. So, this is a very easy idea. You can carry this graph model to computers. Why? Because we want to study it mathematically. How we do this? I will give you some examples before I go to slides. Slides are not moving, so don't worry about them. I haven't started yet. So, my friends, for example, we can form matrices. This is called spectral energy, spectral graph theory, for example, the energy of a graph. It's important in physics and chemistry. How do we form? For example, in the matrix, the term A24, for example, A24 in the matrix. Second row, fourth column, okay? It is 1 if these two vertices, V2 and V4, are connected, are neighbors, okay? If not, then we put 0. So we obtain a 0-1 matrix called adjacency matrix. Similarly, we have incidency matrix. It's more strange. We have Laplacian matrix. We have Zagreb matrix. Different matrices. There are more than 100. In Bapat's book, for example, you can find a list of some very important, more than 100 graph matrices. If you have a matrix, what you can do with it? The first thing, determinant. You can calculate determinant. Second thing, you can calculate some polynomial called characteristic polynomial, okay? A minus lambda I in determinant, you remember, equals to 0. So it's a polynomial. This polynomial has some roots, which are called eigenvalues of this matrix. And because of, by means of these eigenvalues, we can calculate as the sum of their absolute values, the energy of a graph. And people using different kind of matrices calculated different kinds of energies, which are useful for different aims. This is one way. Another way which is more related to my topic today, is using vertex degrees. Each vertex, I will explain it in the talk, each vertex has some degree, which is a positive integer usually, or 0, non-negative integer in general, which is the number of edges meeting at this vertex in a simple graph, let me say first. So basically, in most cases, if there are 3 edges coming to some vertex, 3 edges are meeting at some vertex, then the vertex degree for this one is 3. For example, if it is at the end of some root, it is of degree 1, which is called pendant, because it's not fixed, it's moving easily, okay? It's pendant vertex. So this kind of ideas I will talk. So my friends, vertex degrees are also used. What about the other ways of studying graphs by mathematics? There are lots of graph parameters: chromatography, coloring, domination, these several kinds of labeling, and maybe most importantly, topological graph indices. Why topological? We say it's not topology actually, but topology means not only compactness, connectedness, this kind of nets, this kind of things, but also local structure. So as we are interested with the connections, with the local structure of the graph, we like calling them topological graph indices. These are mathematical formulae defined in terms of distances in the graph, vertex degrees in the graph, or some other parameters, graph parameters, girth, radius, largest vertex degree, smallest vertex degree, this kind of parameters. So there are many ways of studying graphs by computer, by mathematics. What happens at the end, I must summarize now. If we form a graph from a real life situation, like a chemical molecule, okay? Every chemical molecule, for example, if you replace every atom by a vertex, and if you put an edge between these atoms, between these vertices corresponding to atoms, as a bond, chemical bond, okay? Then we form a graph consisting of vertices and bonds, edges, okay? So instead of studying this molecule in the laboratory, you can study in computer. Very easy. No need to form a laboratory, no need chemicals, no need time, no need workers, just mathematicians are needed, okay? Graph theoreticians. So the first example, finally I should say this and then I will go to my slides. The first example of these chemical applications of graphs is due to Harold Wiener. Harold Wiener. It was done in 1947, almost 100 years ago, 70 something years ago. So in 1947, this Harold Wiener wrote a short article. I think it was 4 pages. There is a formula consisting 2 parts as the sum of each part. This formula was given, and it was used to determine the order of boiling points of isomers of alkanes. You know, alkanes, CnH2n plus 2. This is the formula, chemical formula, molecular formula. Okay, CnH2n plus 2, like methane, ethane, propan, butan, pentan, hexane, you know, if you remember this from chemistry lectures. For example, in his example, he gave 3 pentan isomers. 3 pentan isomers. These 3 pentan isomers have the same formula, C5 H12, 5 carbon atoms, and around them 12 hydrogens. Okay, so C5H12. Differently, you can order these. For example, 5 carbon atoms can be ordered as a chain: carbon, 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 or as a chain of 4 carbons, 1, 2, 3, 4, but the second
Excuse me,
or
sir.
third is, yeah.
Sir, actually your slide is not changing, sir.
I know. I have not
Okay,
started to that one.
okay, sir.
In 2
Okay, sir.
minutes,
Okay.
in 2 minutes I will, okay?
You can, sir. You can, sir. Okay, sir. Thank you, sir.
Thank you. Sorry. This way he calculated some formula in terms of distances between the molecules, between the atoms in the molecules. Okay, so for these 3 isomers of pentan, he calculated 3 numbers, and asking to chemists, he was a chemist actually, he decided that if, for example, this isomer is like a chain, that means all carbons are in line with it, with the others, okay, like a chain, like a rope, like this, then the boiling point is lower. But if it is very compact, like a star graph, okay, it's all placed around one point, one vertex, then it is hard to boil it. That means you have to spend more energy to boil this version of pentan. So this idea was generalized to all other chemicals. And now we know that by looking at the molecular structure, that just the orientation or placement of carbons, hydrogens, nitrogens, oxygens, these atoms, in the molecules, we can decide that this is easily boiled, this is hard to boil. Okay, this is an idea. This is an idea due to more than 70 years ago. After that very successful application of graphs to chemistry, many chemists started graph theory. Now, in many countries, there are people who are having chemistry and mathematics, graph theory, PhD in their hands, because both subjects are so much in relation with each other. So now, this is the application of graph theory. Of course, networks, medical sciences, everywhere, social media like Twitter, like Facebook, you have followers, you are following people. So between you and the other people, there are relations. You know someone, or you follow someone, or you don't follow someone. In the first case, you are connected by an edge. But if you don't follow this one, then there is no line between you. Okay, so if you are a very popular person, there are lots of lines, edges around you. Okay, but if you are an alone person, poor people, then there is no line between people and you, only or few ones. Okay, just relatives and close friends. So this shows the popularity, this shows the effectiveness, this shows the richness, whatever it is, the idea. Okay, so graphs are, just by looking at them, give you some idea, but if you work if you use mathematical instruments, tools to study them, you have deeper information, deeper knowledge about the real life situation. So now, on the second part of my talk, I will move to some more graph theoretical ideas. We have now some idea about applications of graphs, which are really a lot, because of this, there are lots of graph theory papers nowadays. In general journals, there were maybe a few before, 10 years, 15 years, 20 years ago, but now almost a half, maybe more, are on graph theory and its applications. So it's becoming very popular. So my friends, I will give you some fundamental ideas first in my talk, the rest of my talk. Then I will give you some motivation why we defined this graph invariant called omega invariant 5 years ago, 6 years ago almost, and how we can use to solve many unsolved problems in graph theory by omega invariant. In the middle, in the midway, I will give you 4 or 5 questions with answers, don't worry. So we will see that how big problems can be solved by omega invariant. Many people actually now are applying omega invariant to their subjects if they can find some connection. And of course, I should say at this point, if you have some idea after listening omega invariant from me, you can search in Google, of course, for the papers. There are more than 60, 70 papers now, some PhD theses. Lots of people are working on omega invariant. So it is a popular subject nowadays in graph theory. So you can contact me anytime for any questions or any ideas. I'd like to explain more because in limited time, I can just talk about the fundamental things. So, for this figure, this is a graph, the first graph in our talk we see. So, there are some black dots, you see, called vertices, and between these vertices, you see the edges. So, a graph consists of some vertices and some edges. At least one vertex we should have. It cannot be empty set. And sometimes no edges are possible. No one knows each other, so it's a new idea, like the movies. You know, when you wake up, you are in a new environment. Science fiction movies, you know, it's like this. You don't know each other, so there is no edge. Okay, very natural. So this vertex is labeled by 4. Why? You can easily guess, even if you don't know graph theory, because it's connected to this vertex, this vertex, this vertex, and this vertex. It has 4 incident edges, okay? Or 4 neighboring vertices, 4 adjacent vertices. This one, this one, this one, and this one. But this poor vertex, has only one neighbor. So it has of degree 1. This is called, as I said before, pendant vertex, because it can easily move. It's not fixed very well, okay? Just one point it's connected. So if you push this vertex on some side, it will move easily. But this line is fixed at these vertices, 2 vertices. It is easy. It is not easy to move it, for example, like a line. So, my friends, I will go to the main part now. These vertex degrees form a set like this. 1, you see, this is the multiplicity, twice. 1 appears twice. 2 appears once, okay? So 2 appears once. 3 appears twice again. So 3, the vertices of degree 3 are 2 in number. And there are 2 vertices of degree 4, this one and this one. So in total, 2 plus 1 plus 2 plus 2, which is 7. 7 vertices are there. But this setting do not give you direct information about the number of edges or the number of triangles, the faces, okay? This is a, not triangle, of course. This has 4 vertices. So it's a kind of square in our terms. So this set is called degree sequence, okay? So naturally, it starts if there are not isolated vertices of degree 0, which we don't like this case. It starts with some 1s, some 2s, some 3s, some 4s, and the largest vertex degree, which is 4 in this figure, is denoted by capital delta, okay? And there are A delta times the largest. For example, A delta is 2 in our case because the largest vertex degree has multiplicity 2. So my friends, for some graph, for some figure, you can easily write this set, this degree sequence. But on the contrary, if you are given this set, can you form this graph? This is the first question. If for such a set, okay, for such a set of non-negative integers, we can draw at least one graph, then we say that this graph is a realization of this set. And this set is called realizable. Realizability is very important in graph theory because randomly your friend gives you some integers 1, 1, 2, 2, 3, 3, 4. Can you make a graph out of these numbers? In this case, yes, but in many cases it may be no. The numbers should be given carefully, okay? There are rules for this. Most well-known tests algorithm for the realizability is Havel-Hakimi. Havel is a Czech mathematician and Hakimi is Iranian mathematician. There is 7 years between the times they defined this algorithm, but independently they did. So this we call it Havel-Hakimi process. You can search for it. So given some numbers like this, 1, 2, 2, 2, and 3, it gives you an algorithm to decide whether by these numbers you can draw a graph like this or not. So there are more than 10 tests that are available for researchers. So for realizable degree sequence, that means there is at least one graph. The second number is how many graphs are there? For these numbers, we can form this graph, you see, and we can form this graph which are not isomorphic. This has triangle, this is a square, for example. So that means these two graphs are different, but they both have the same vertex degrees, 1, 2, 2, 2, you see, and 3. So that means for such a set, we can have more than one. In this case, at least 2, we can say, at least, because not we should not say 2, because there may be others. These are the given ones to us. In fact, there are maybe 5, 6 more graphs we can form by these numbers, okay? But you can put some conditions. You can say simple graphs, for example, you can look for. Connected graphs. This kind of conditions, of course, eliminate and reduce the number of required graphs, okay? So this is another problem. At the end of my talk, I shall be talking about this problem. For some set of integers, non-negative integers, how many graphs we can form if the set realizable. So this is the final part of my talk. So my friends, next, this is the motivation my student, PhD student, had in defining omega invariant. This is a new invariant, actually. It's like Euler invariant. If you know topology, graph theory, differential geometry, algebraic topology, Euler invariant is very important. in classifying, for example, orientable or non-orientable surfaces, this kind of surfaces. For graph theorists, every graph can be embedded, can be drawn in different spaces. You can draw it on the sphere, on the plane, on the torus, on the double torus, on projective plane, on Klein bottle, different ways there are. But the classical thing is there is an invariant number for all graphs drawn at these spaces. If you draw it on the sphere, then the Euler characteristic is different. If you draw on torus, then the Euler characteristic is 0, for example. So this kind of decision making is possible by these invariants. So let's continue. In trees, tree means like a graph like this, without any closed area. There is no closed area, you see. You cannot hide anything inside some square or triangle, for example. So this is called a tree. There are two conditions. It should be connected in one piece. From every vertex, you should reach to other vertices by a path. And the second condition is there is no closed regions. Okay? Here, for example, there are closed regions. Here, there are 3 closed regions. 1, 2 triangles, and 1 foregons. Okay? So this is a tree. Trees are very important because in every area, in computer science, in tournaments, in our lives, always there are yes and no's, the algorithms. We use trees because at each vertex, we have to decide either to go to this way or to go to this way, okay? So this number A1 of pendant vertices, these, okay, is related to other vertex multiplicities. This is the number of vertices of vertex degree 3. For example, in our case, it is 0. Also, A4 is 0 because there is no vertex of degree 4, but there are 2 vertices, I equals to 1. Let's start from the beginning. We get minus A1 here, you see. If you put I equals to 2, then the coefficient is 0. So there is no A2, you see. A2 is not appearing here. I will explain, if I have time, geometrically why we don't have any 2's, okay?
Before we
Then
proceed, I've posted a small link in the chat box.
Times A3.
It is a small quiz with 20 questions
times A4,
based on the
A4.
session that
5
I have
minus
handled.
2, 3 times A5.
You can answer, try to, it's an objective type quiz. You can try to answer this quiz for your refreshing what you have gained from my session.
1 is strange, it's minus 1, and 2 is not appearing at all. These are
on behalf of the management,
distinct cases.
our beloved administrator, Reverend Sister M. Devi, our respected principal, Dr. R. Rubin, and the organizing team, it's my privilege to propose the vote of thanks for the day.
Gives to us,
Gratitude
now
and respect
I will
goes
talk about.
for our distinguished
Before I will
guest
talk
speaker,
about this omega
Dr.
invariance
Preeta
applications,
S.,
I
for
will
not
give
only
a
sparing a
few
valuable
main
time, but also
properties.
for enlightening
There
us
is
with a
another way
commendable
of
talk on the
defining
subject.
this number.
My heartfelt
Okay?
thanks goes
If
to
you
our
know
beloved
the number of
administrator, Reverend
edges
Sister M.
and
Devi,
if you know the
and
number
our
of
honorable
vertices,
principal
the
for their
size and
constant
order of the
support and
graph,
encouragement.
then omega is also
We are much
equal to
obliged
twice
to the
m minus
IQAC team
n.
of
Of course,
SJC for
these
organizing such
being
an enlightening
integers,
session. My
this
thanks
number
also
is an
goes to the
even
system
integer,
admin
always,
and his team
because
for
this
the
is
technical
the
support.
number of something,
I owe
this is
to
the
the
number of
participants of the
something,
day for making this
vertices and
session
edges.
and
So
wonderful one.
twice an
Lastly, I
integer
thank all
must
of
be an
you for
even
your
integer.
participation.
So omega
Thank you.
is always even. This is something to remember.
ma'am.
Omega
all
cannot
of
be
you to
1,
turn on the
cannot
video
be
for the
5,
photo session.
cannot be minus 7. Okay? It should be 0, 2, 4, 6,
I
or
once
minus
again
2,
posted
minus
the
4,
link.
minus
Please
6.
try now.
We have to remember this. We have classified, my friends,
I request
all
the
the graphs.
to turn on
There's
their video
large
for the photo session.
popularity of graphs. We have classified all graphs into 3 classes. One is the ones with omega equals to -2. It looks very small family, but it's not. All 3 families are equally large. In the middle, we have graphs with omega equals to -2. On the right-hand side, omega is greater than or equal to 0. And on the left-hand side, omega is less than or equal to -4. -2
Thank you all.
is one class.
Please fill the
0,
link which has
2,
been given
4,
by our
6.
resource person.
This is one
We have
class.
posted that in the YouTube as well.
-2 here in
feedback
the
link
middle.
will be posted now.
-4, -6. It
Please
cannot
fill
be
the
odd
day 3
number.
feedback come
I
attendance
have to
link
repeat
as soon as
again.
possible because it will be filled by
-4,
4:30
-6, -8, -10. These graphs are having
Thank you so
the
much,
same
Preeta ma'am.
properties. So 3 groups of graphs,
Really,
3
we had a
families
very
of
wonderful
graphs.
session.
For
It was
each
very
family,
useful.
for each
Thank
three
you.
of
so-
Can I
for each
leave?
of these 3 families, we have different algorithms.
Can I
We
leave?
have different methods.
Yes, ma'am. Thank you
we
so
have
much,
different
ma'am.
Thank you
theorems.
so much. Thank you.
For example, when you have omega equals to -2, very
Participants,
important
we have
number
posted
is
our
-2.
international
And
conference
if you
brochure
want
on
a
the
simple
registration link
connected
in the
graph,
WhatsApp group,
it
and we have
must be a
posted in the
3.
YouTube as well today.
Similarly,
So,
for a 3,
all of you are welcome for
omega
our
must be
international conference,
-2.
which will be held
If
on
you
27th
calculate
of March.
omega for this graph, which is 3, you don't need to do anything.
Thank you
because
for
it's
your
a 3,
participation.
you know that
We expect the
omega equals
participants
to
tomorrow at
-2.
1:55
But
p.m.
for these ones, omega is
Meet
not
you all in
-2.
tomorrow's
Omega
day
is
4
0
session.
for these
Thank you so
ones.
much.
Okay, we'll see. So, my friends, the second result is about the number of faces. The number of faces. For example, in trees, no faces are there. Here, each graph on the left and on the right have one face. Here, we have 3 faces, I explained before. So, the number of faces can be calculated before drawing it, because you don't have the drawings. If you have figures, if you have the shape of the graph, then it's easy. 1, 2, 3, you can count easily. But looking at these numbers only, 1, 2, 3, 4, okay? If you don't have a picture of the graph, then you don't know what will happen. Okay? Lots of different graphs are possible. What they have in common, one of them is the number of faces. The number of faces is equal to this number, omega a half plus c, which is the number of components. If your graph is connected, every vertex is connected to each other vertex, the other vertices, then c is 1. But you have a network of 3 towns. Okay, one town has its own network, one town has its own network, and the third one also. So these are not related to each other. So one piece of the graph here, one piece here, one piece here. So the graph, our graph, which is a network, consists of 3 parts, 3 pieces. So these are called components. So you have to put C is 3. I will give examples. Okay, my friends. Again, okay. Problems. I mentioned about some problems before I finished with the answers to them. What is the first problem? You are given some set of positive integers. The largest integer is 7, only once appearing, then 5, then 3 4s, 3 3s, 1s, 2, and 3 pendant vertices. So, for these numbers, for these integers, people ask you, it's like a puzzle, okay? Can you draw a graph with these vertex degrees? You should have one vertex which is connected to 7 others. You should have another vertex which should have 5 connections, and etc. Okay? So this is realizability. Can this set be realizable? Okay, realized. What is the cyclomatic number? Which is the number of independent cycles, the phases, okay, of any connected. C is 1, don't forget. The problem is, again, this set, the same set, you see. So if you calculate omega, how we calculated omega, you remember, this is A1, 3. So it goes at the end as -3. -3 we have. 2 does not appear, so 2 minus 2 is 0. We don't care about this number. 3 minus 2, 1 times 3. 1 times 3 is 3. 4 minus 2 times 3, 2 times 3, 6. So 3 plus 6, we have 9. Don't forget -3 here. Then 5 minus 2 times 1, which is 3 again. So we have 9 plus 3, 12. 7 minus 2 is 5 times 1, which is 5. So 12 plus 5 is 17. If you remember -3, then 17 minus 3, which is 14. It's not difficult. It is very easy. Primary school students can do it. Just some integers, you put them in the formula, okay? So, as this number is even, we are happy because this set is realizable. How? We don't know. Also, what was the cyclomatic number? The question says, what is the cyclomatic number? You see, the number of phases. If you remember the formula, it is omega half plus the number of components. As it says connected, C is 1. So this number is 1. Omega is 14. 14 and a half plus C is 8. So that means if you draw this graph, out of this set, you will have exactly 8 phases. Not 7, not 9, not 5, not 10. Okay, exactly 8. How many graphs can you can draw? Each of them will have 8 phases. Okay. So second problem, my friends. Once you are given such a set, okay, you can have connected realization or disconnected realizations. Both are possible. We don't know the rule at the moment. We will learn. So if you are given some set of integers like this, you don't know about the realizability, you don't know about the number of phases, you don't know about anything. How many of them are there? Okay, are they connected or not? So in many theories like Diophantine equations, number theory, we put some restrictions because our computer cannot work up to infinity. We have to put some bounds from lower to upper bounds, okay? So if you restrict your set, then you are free to calculate, you are easily calculating this, whatever is needed, okay? This information. In our case, if you know minimum and maximum number of components for this set, you remember this set is given, you form a graph. Your friend, you look at the picture he drawn, it is different. The other friend has drawn anything else, something else, okay? So many people can form different graphs. One might have triangles, the other might have no triangles, for example. One might draw connected graph, some others may draw disconnected graphs, for example. So what we know, maximum and minimum number of components is important. Both of them are important for us, okay? So this is lower bound, then I will give you upper bound. Lower bound is minus omega divided by 2, okay? As omega equals to 2 times m minus n, okay? If you put 2 times m minus n, 2's are cancelled, and minus, it will become n minus m. because it was 2 times m minus n. Okay, so this is lower bound. This is lower bound. If you can calculate omega, then you know that these graph realizations you draw, the others draw, many of them are there, will have at least this much components. If it is 1 or smaller, that means the number of components could be 1, which means you might have connected realizations. But the lower bound appears to be 5, for example, then that means the number of components is at least 5. Then that means you cannot have connected realization, or a realization with 2, 3 pieces or 4 pieces. The lower possible number, lowest possible number is 5. Okay, this is the idea. So for our example, omega is 12. I don't calculate it again. Omega is 12. You can do it if you want. By corollary, the above corollary, we calculate minus 12 divided by 2, which is minus 6. Of course, c is a positive number. C is a positive integer. So knowing a positive integer is greater than or equal to minus 6 has no sense. So we take it automatically as 1 because it's at least 1. It could not be minus or 0. It's number of some components. So C can be 1. That means some realizations could be connected. But maybe C could be 2 because knowing it's at least 1, it means it could be 2, it could be 3, it could be 77, whatever, okay? So it could be disconnected as well for the moment. My friends, this was lower bound. What about the upper bound? Upper bound is this sum. This is the formula. Very basic formula, actually. Very easy to obtain. Very clever formula. You calculate the sum of AIs. AIs are, you remember, multiplicities of these vertex degrees. For even vertex degrees like 2, 4, 6, 8, 10, okay, we don't know what is the maximum one. We sum up, we add up all these multiplicities, A2 plus A4 plus A6 up to wherever it goes. Plus, the second part is multiplied by a half. And it's taking the same sum, but over all vertex degrees, like A1 plus A3 plus A5, but you must multiply this sum by a half. So now going back to our example. This is our example, okay? 3 to the 4, 4 to the 2, 5 to the 2, 8 vertices, you see. So what is the maximum number of components, maximum number of C components, okay? So we had 2 sums for even vertex degrees, which is even here, 3, 4, 5. 4, of course. So what is the multiplicity of 4? 2. So you write 2 here in place of this sum. For the second sum, we look for odd vertex degrees. And we add up their multiplicities, A1, A3, A5, A7, and multiply them by a half. You see, what are the vertex degrees which are odd? 3 and 5. What is the sum of their multiplicities? 4 plus 2. What we should multiply them with? A half. So we get 5. So my friends, given these 8 positive integers, you have to draw some graphs. Believe me, there are more than 100, maybe 1,000. What is the minimum number of components? 1. What is the maximum number of components? 5. So this is an example of 5 components. You see, this is one component which is not connected to others. This is another component. There are 5 components here. This is a vertex of degree 4. You see, can you imagine this? This is a vertex of degree 4. 1, 2, 3, 4 edges are meeting here. So this is a vertex of degree 4. This is another vertex of degree 4. This is a vertex of degree 3 here. 1, 2, 3. This is not a simple graph, so the definition I gave you at the beginning, which is mostly acceptable, is not correct here. This is not a simple graph. Simple graphs contain no loops nor multiple edges. Okay? These are not important for our talk, so I'm not going into detail. This is a vertex of degree 5. You see, two 5s are connected to each other because there is one edge here, one edge here. Actually, they are the same edge, which is a loop, but locally, if you zoom in, then there are 5 edges meeting at this vertex. So for us, it's important. The degree is 5. So the third problem, my friends, how we can decide whether a realization is connected. This is an open problem. This was an open problem in graph theory. You are given some positive integers. You can form some graphs out of this set of integers, but you have to know, you are wondering about whether they will be connected or not. I've been talking about this for some time. So, for example, for this set, carefully look at these two pictures, two graphs. This has one vertex of degree 4, you see, and another one exactly the same. So two vertices of degree 4 and around 1, 2, 3, 4, 5, 6 vertices of degree 1. So this set can be realized like this as a connected graph. This is the same, degree 4, and this is of degree 1, 1, 1, 1, 1, 1, okay? So 6 vertices of degree 1, 2 vertices of degree 4. But this one is different from this one. This one is disconnected. So what we have so far, according to this connectedness related to this idea, for this set, we can have either connected realizations or disconnected. Both are possible. So the question is, what can we guarantee? The main result is, very important result, answering an open problem in graph theory is this. If you calculate omega, which is easy, as I said, omega is less than or equal to minus 4, okay, minus 4. This was one of the graphs, one class of the graphs, okay? Minus 2, larger and smaller. This is the smaller part. If you get omega equals to minus 4, if you get omega equals to minus 6, minus 8, minus 10, then all realizations, all graphs will be disconnected. That means you cannot have any connected picture. At least 2 pieces or 3 pieces, we don't know. Okay, so, and if omega is a minus 2 at least, or equal to minus 2, then the graph is potentially connected. That means both connected are disconnected. Okay, most of the degree sequences can be realizable in many ways, so this is an important result. Looking at omega invariant, just a number, it gives you about connectedness of all the graphs you will have. It gives you the maximum number of components, minimum number of components, lots of information, the number of faces you will have. So if you have these tools, and if you work with some networks, if you work with some chemicals, then you can easily decide about topological structure, local structure of these ideas, these examples. For our example, omega equals to minus 4 means all disconnected. All are disconnected. So that means this is, for example, one picture for this graph, okay? 2 pieces, because the number of components, if you remember, was minus omega a half. omega is -4, so that means -4 plus 4 divided by 2 is 2. So this is the smallest number of components case, 2, which is 2. But you can also draw this graph like this. The same vertex degrees they have, okay? For example, this is a vertex of degree 3. Here there is a vertex of degree 3. Actually, there are 3 of them. Here there is 1, there is 2, there is 3, okay? So that means the same vertex degrees are here and here. But if someone gives you $1 million and asks you to draw these numbers as a connected graph, then you don't work for it because you know that it's not possible, okay? And finally, how we can find connected realizations. I will skip this part and just say a few words. You remember, we have classification, -2, larger and smaller. For each case, we gave algorithms about how we can obtain some realizations, okay? So for -2, for example, we know that it will be a tree. So for a tree, you know, we have several structures like caterpillar trees, crab trees, this kind of different things. And we have some algorithm. For smaller than equal to 0, then we have another algorithm. And for the other part, we have another algorithm. So we know how to form our graphs. For example, if omega equals to 0, in our case, it's omega equals to 0, then we know that we add these 2, 3, 1, 2, which are 2, 3, 1, 2, except once, okay, the multiplicities of 2, 3, 4, 5, 6, 7, whatever, okay? So non-pendant vertices, the number of non-pendant vertices, which is n minus a1 actually. So this is the maximum cycle length. Cycle length is also important because in Eulerian problem, in Hamiltonian problems, we have to look for cycles, circuits, okay? So if you know that the length of your cycles in the realizations could be minimum 5, maximum 8, it is an important, very valuable information. So my friends, it could be maximum 8 and it could be between 1 and 8. The cycle length could be 1 means there is a loop. The cycle length is 2 means there are multiple 8s. After 3, it's easy. You know the classical idea: triangle, fourgon, pentagon, hexagon, this kind of up to octagon you can form in our example. For example, this is the first case with octagon and with 7-gon, with 6-gon, with 5-gon, pentagon, with square, with triangle, with 2-gon, and with 1-gon. The same set and different realizations, you see. This I will skip because it's boring a little bit. Another application of omega, because sometimes we have some old theorems, like 1964 Edmonds theorem. It gives you potentially connectedness condition, if and only if, okay, by means of some inequality. So omega invariant says that the same condition is just omega is greater than or equal to -2. Okay, so if you apply Edmonds theorem, you have to do these calculations. Not too much, but not too less. If you apply omega, just one line. Okay, so sometimes we can modernize, we can compactify, we can make more effective the existing results. Okay, this is another application of omega. And finally, in 2-3 minutes, I will be giving you what we are doing now about omega invariant. There are lots of problems, but this is the main one. We want to determine as I explained at the beginning, the number of realizations of some given degree sequence. Out of this degree sequence, how many graphs we can form without any conditions. This is very hard problem. If you put some conditions, like connected realizations, like simple realizations, like realizations having 3 components, like realizations having 5 components, like realizations having 5 faces, okay? These all make problem easier because restrictions are good. In general, not, because your paper will be restricted. You couldn't find the general problem. You could solve the answer to the general problem. But in this case, what we do as plan B, we put some restrictions. This is mathematics. So what we do is, I will give you some figures again. We calculate, I don't go into details, we gave an algorithm. We calculate Cmax. Cmax, if you remember the sum, 2 sums, vertex, or even vertex degrees, odd vertex degrees, a half. Remember the formula. So C maximum is new. Cmax is easy to calculate. So we know Cmax. Usually it is 1 or 2 or 3. Very easy. Okay. Then we know that maximum number of components, let's go to my example. Cmax is 5 for some degree sequence. What is the degree sequence? You can count 2, 2, 4, 6, 8. 2, 2, 4, 6, 8. Okay, this is 5 vertex degree sequence, 5 vertex degree set. Okay, so this is maximum number of components. The second step, we do try to connect 2 components, any 2 components. Okay, for example, in the first one, you see 5 components. Here we have 4 components because 2 smallest components, red dot and black dot, are combined into each other. Okay, they form a new component with 2 vertices. Before, they each had 1 vertices of degree 2, Here again, this is of degree 2, this is of degree 2. So the degree sequence is not changed, but the number of components is reduced from 5 to 4. We do this in all possible ways. You see, for example, the last one, we combine these 2 largest ones, a vertex of degree 6 and a vertex of degree 8. They are, you see, this is a vertex of degree 8, this is a vertex of degree 6. They were combined into each other. So these are all possible ones. We count their numbers, but this is the hardest part of the algorithm. We have to check whether in different routes we could have the same graphs. For example, this third one you see on the left, okay, is the same with this one. If you look at carefully, just the order of these 2 are changed, okay? The colors are not important, the vertex degrees are important. So my friends, we have to eliminate one of them by just cancelling out. So after eliminating, we calculate the total number of all realizations having 4 components. What we do next, for each remaining one, we have to calculate the number of realizations of this set with 3 components. Next, we combine 2 of them again. So we have to search in which ways, what vertex degrees, what components could be combined into each other. This is not always possible, okay? So at the end, we add up all these numbers to get the required number. For example, at one stage, if you put some condition, like there are k different entries in the vertex degree set, degree sequence, and there are T entries with multiplicity at least 2, which is less than K. Then, for example, the number of components with the number of realizations with 4 components in our example, because 5 minus 1 is 4, you will get K over 2 combination number plus T. This is, for example, one of the results we obtained. I will not go into details, I don't have time. So, like this, we obtained several formula. This is a condition. All are having even integers, like in our example. Okay. In examples, there will be odd vertex degrees. This is not valid for odd vertex degree case. Okay. If there is at least one odd vertex, then this theorem is not correct. This is if you have all vertex degrees 2, 4, 6, 6, 8, 8, 10, 12, like this, then you can apply this theorem. For the other one, for odd case, we have some other results, or we will have some other results. We have not computed yet, okay? Just by putting some conditions, some restrictions, we obtained some sub-cases solutions, but soon we hope that we will get the main results. So, my friends, this is the first paper in Turkish Journal of Analysis and Number Theory. It was called A New Graph Invariant. This gives you the definition and motivation. The second paper next year was Extremal Problems on Components and Loops in Graphs, again. Then Omega Invariant with Cyclicness. This is Edmonds' theorem I mentioned. This is Havel and Hakimi's papers. Okay, let's move to the next one. Okay, this is matching number and omega invariant. This is connectedness and omega invariant. This is nullities and omega invariant. This is topological indices and omega invariant. This is cyclicness and omega invariant. You see, in every paper, there is a different idea about graphs, like connectedness, like cyclicness, like topological indices, and it's related to omega invariant. You see lots of join and corona products, this kind of ideas, which can be combined easily by omega invariant. So I will stop here, my friends. These are all some of the recent publications. There are more. If you have any questions, maybe you will not have any. Usually people are listening the first time and they don't have many questions. But if you think that you might relate your studies, your works with omega invariant somehow, which is really possible, then you always can contact me and you can send me your ideas. I would be very happy to answer your questions and suggestions. Thank you for listening, and thanks you for the invitation again for the organizers.
Knowledge is love and light and vision. Wisdom is knowing what to do next. Skill is knowing how to do it. Virtue is doing it. Yes, you did it, sir. Thank you for the informative and innovative session. Gratitude makes sense of a past, brings peace for today, and creates a vision for tomorrow. I request Dr. A. Maheshwari, Assistant Professor, to deliver the vote of thanks.
It gives me an immense pleasure to deliver the vote of thanks for this faculty development program. I would like to express my sincere gratitude to our chief guest, Professor Dr. Ismail Naci CANGUL, who despite his busy schedule has found time to grace this occasion. It was very innovational and inspirational thoughts. Thank you, sir. I would like to thank our beloved principal, Dr. Yan Muthumani ma'am, for her support and guidance. Thank you, ma'am. I would like to thank Mr. V. Ratnakumar, Assistant Professor and Head, Department of Mathematics, for his unwavering support and encouragement. I express my sincere gratitude to all the heads of the departments and staff members of PPG College of Arts and Science for their everlasting stimulation. I extend my sincere thanks to our participants for their combined effort to make this program a tremendous success. Once again, I thank you all.
Thank you, ma'am. Dear participants, I request you to kindly fill the feedback form, which is posted in the chat box. Thank you all for the utmost cooperation and support. You all can leave the meeting once you fill up the feedback form. We are expecting your presence for a session 2 at 6:15 p.m. today. Thank you all. Thank you so very much, sir.
Thank you. Thank you. Take care. Hope to see you.
Thank you so much, sir. Have a good day.
Thank you.
Dear participants, I request you to kindly fill the feedback form, which is posted in the chat box. You all can leave the meeting once you fill up the feedback form. Thank you all.